start. Okay, and so by way of review, I thought we would start by remembering what the postulates of quantum mechanics are, with some additional commentary perhaps in places now that we know something about applying them. Okay, so the first postulate has to do with what's the state of a system. And the state of a system is represented by and associated with a non-null ket, which we might call psi, in a complex linear vector space with an inner product. So all of those things are important. And what we mean by them is, first of all, complex just means that if you've got a state, you can multiply it by a complex number. And linear means you can add them, and then they obey all the usual addition properties. Okay, and the fact that it's a vector space means that you can find a basis for all your states. And the inner product means, well, we write it like this. Psi1, psi2 is the inner product between two states. And importantly, it's a complex number, not a real number. Okay, but in the special case where you take the inner product of a state with itself, okay, then that is real. And not only is it real, but it has to be positive, unless your state isn't a state. So unless the state is the null ket, which will happen in arithmetic operations. Sometimes you'll do something and you'll find some expression is equal to the null ket. But if so, then it's not a state. And then furthermore, a ket psi, and we said we could multiply by a complex number, so we can, but mathematically those are different, but physically they're the same. See, these are the same physical state. Okay, and so you might say, well, then if they're the same physical state, why don't we just decree that as a postulate that psi has to have unit norm, because that's often what we do anyway. And some books actually try to do that, but I think that's a mistake, and a tactical mistake, not a mistake of that is going to lead to some contradiction. But there are three reasons, at least that I can think of, not to just define that the norm of a state is 1. And they're all sort of practical things. The first one is that some kets can't be normalized. And so examples of kets that can't be normalized are, I'm going to turn off my video here. Some kets that can't be normalized include eigenstates of momentum and position. So those are idealized states. They don't actually exist as physical states because they don't have finite norm. But they're very useful as tools that we use for idealized situations. Okay, A second reason is because, as we will again mention shortly, there's one important operation that doesn't preserve the norm of a state, and that is when you make a measurement, which we'll get to in a moment. So the norm changes when you make a measurement. Of course, if it changes, then you can change it back to have norm 1, but as an intermediate step, you don't want to, it will change when you make a measurement. Okay, and those are things that we saw in the last semester, but there's one that we will encounter this semester that we haven't encountered yet, and that has to do with a process of perturbation theory. And when we do perturbation theory, we will find out that it is overwhelmingly convenient not to use norm 1, but to use some other finite norm. And even in the intermediate steps, we won't actually know what the norm of the state is until we get to the end of the problem. So perturbation theory uses states that don't have norm 1. And we'll find out that there's a really important and good reason why we want to do that. Okay, but we will get to that later. All right, so that's all I wanted to say about postulate 1 for now. Postulate 2 has to do with observables. Okay, and observables are Hermitian operators. But we also learned that not just any Hermitian operator can be an observable. They must also have the property that the eigenstates of the Hermitian operator have to form a complete basis. Otherwise, it's not an observable. So it can be chosen to be a complete orthonormal basis. And that's too many syllables and too many letters. So from now on, instead of saying complete orthonormal basis, I will usually just say orthobasis. Or if at the moment it doesn't happen to be important to us that it's orthonormal, I might just say basis. Okay, and so if I've got an observable A and it acts on some states that I label by, let's say, alpha, where alpha is the eigenvalue. And then there might be some other label that I need to tell apart the states with different eigenvalues. So it looks like this. Okay, and so A is our observable. And alpha is our label or eigenvalue. We don't have to choose the eigenvalue for the label, but it's usually convenient. And then rho sub alpha is our degeneracy or redundancy label. I think last semester I tended to call it redundancy label sometimes, but I've rethought that. I think degeneracy label for alpha is a better thing to call it. Okay, and so those are the eigenstates, and orthonormal means they have to satisfy this, that if I take the inner product between any two of them, I'm supposed to get 1 if and only if all the labels are the same. So alpha and alpha prime have to be the same, and rho sub alpha and rho prime sub alpha prime have to be the same. Okay, so that's the orthonormal part. And it should be mentioned that alpha and rho sub alpha might not just be numbers, they might be lists of numbers. So we're using a notation where that is a possibility. Okay, and then they're complete. Complete means if we sum over all of them, with an outer product, so that means we do this. Okay, then we get the identity operator. The identity operator is I, and so this is orthonormal, and this is complete. And so it's possible to invent Hermitian operators that don't satisfy this. And if you find such a thing, it is not an observable. Okay. Now, I mentioned this case of idealized things that you can't, idealized states that you can't actually make norms of. And those tend to correspond to cases where alpha is continuous. So just because they're not technically legal doesn't mean we're not going to talk about them. For example, position. Okay, but then we just remember that instead of say taking a sum, everywhere you see a sum, instead you do an integral. And every time you saw Kronecker delta, you instead do a Dirac delta function. And in those cases, this is called Dirac orthonormality. And as Dirac himself emphasized again, this is technically not a Hilbert space, but it works so well that we do it anyway. Okay, and then if rho sub alpha, the degeneracy label is continuous, then the same thing. So we would do, instead of a sum over rho sub alpha, we'd do an integral over it or the list of them, if there's more than one of them. And if we had a Kronecker delta, something like that, then we should replace that by a Dirac delta. Okay, so postulate 3 says what the allowed results of a measurement are. So if I ask you to find the probabilities for different measurements, one thing to do is make sure you know what all the allowed possibilities are. Okay, and so if I measure A and it has eigenvalues, alpha, then those are the possible results. So this is why it's important to be able to find the eigenvalues of any given operator. A lot of times that means representing it by a matrix and then finding the eigenvalues of the matrix because they're the same thing. But not always. Sometimes it's a differential equation. And so, for example, if your observable is the position operator x, and we do operators with capital letters, that has eigenvalues that we're calling little x. If it's a three-dimensional position operator, then that has eigenvalues that are the three-dimensional vectors. That's an example where your eigenvalue is a set of numbers rather than just a number. And if you have an angular momentum, for example, the z component of an angular momentum, that has eigenvalues h bar times the magnetic quantum number. And we found that m had to be an integer divided by 2. And if it's orbital angular momentum, it actually has to be an integer. Okay, so that's postulate 3. Postulate 4 tells us what happens or what the probability is when we do a measurement. So if you're in a state psi and you measure an observable A, then the probability of getting any one of the results, so the results are the eigenvalues alpha, is, and we're going to use curly P for probabilities. And so what you're instructed to do is sum over all the degeneracy labels for that possible outcome of the complex square of the matrix element. And the key thing to remember here is that the postulate tells you that you sum after squaring, not before. In the situation where you have to sum over redundancy labels. This is also equal to just a different way of writing it is this. So you sandwich a projection operator in between the state in the matrix element. And the projection operator that one puts in there is a sum over the degeneracy labels of alpha, rho alpha, alpha, rho alpha, corresponding to the measurement that you made. And among the properties of a projection operator are that if you square it, if you do it twice, it's the same thing as doing it once. Okay, and everything I wrote up there assumes that the norm was 1. So if it's not 1, then you might have to divide by the norm. So otherwise, the probability is the same thing. But now you are dividing the whole thing by the norm of the state. So one situation where that might happen is, for example, if you are actually working with a state that you can't normalize, like an idealized momentum eigenstate. And so then what you'd usually do is you'd write down a formula like this. Okay, and this denominator won't be well defined, but then you can do something like put your system in a big box, and that will make the norm be well defined again. And so then you can actually evaluate this and evaluate the numerator, and everything will make sense. But in intermediate steps, it's convenient to write it this way, where you don't have to deal with the messiness of putting the system in a big box. Okay. All right, postulate 5 is the controversial one, the one that people have for decades. Many people have been trying to get rid of this postulate, and that's the collapse postulate. So the collapse postulate says that after you make a measurement, what is the state? Okay, so if you got the result alpha, then the state after the measurement is the projection operator referred to in the previous postulate acting on the state. Okay, and that is what is almost always not normalized.
I'm sorry, Professor.
Yes.
I fell behind again. 2 lines above number 5. Is that note?
Yeah, sorry.
Okay.
Very good. Okay, other questions? Okay, so if you do this, then assuming the state that you end up with is normalized, is not normalized, but can be normalized, then there's a normalized version of this. Which is you just take it and divide it by the norm of the state after the measurement, which is square root of psi p alpha psi. But p alpha is p alpha. Okay, and so this is p alpha psi over the square root of psi p alpha psi. Okay, but then again, that assumes that your ket is actually normalizable. If it's not, you might have to do something like put the system in a box. And we'll end up doing that in a few cases that we'll deal with this semester. For example, when we treat the photoelectric effect, we will be putting our system in a big box temporarily, And then what usually happens, or what you want to check, is that after you're done with the problem, you can take the size of the box, some value, and if you want to, you can set it equal to 10 light years, and the answer to your problem shouldn't depend on the size of the box if you take it to be the limit where it's very large. Okay, and then the last postulate has to do with time evolution. Okay, and that says the state just obeys a differential equation. Psi of t is equal to something called the Hamiltonian. Okay, and you could say, what's the Hamiltonian? And it's sort of a circular definition, but the Hamiltonian is whatever it is that makes this equation be true. Now, you can also try to define the Hamiltonian by looking at the analogous classical system, but the flaw in that is that not every quantum system actually has a classical analog. And so I think it's actually better to say that this equation defines what your Hamiltonian is. But the eigenvalues of it are what we call the energies. And they usually correspond to what we would classically call the energy. Now, one thing that we will get into later this semester is that we're taking this as a postulate, but some people would say that this is really what's known as the Schrödinger picture of quantum mechanics. And so later on, we will be discussing Heisenberg picture and Dirac picture, otherwise known as the interaction picture, in which the state of the system does not obey this equation, but it's equivalent to this equation. And so implicitly, when I'm saying this is a postulate of quantum mechanics, I'm saying this is a postulate of quantum mechanics in the Schrödinger picture. But the point is, it's equivalent to any other picture that you might want to define.
Dr. Martin, I have a quick question about that.
Yeah, sure.
So are the different pictures kind of like the classical analog to different formulations of, like we have Newtonian mechanics and Lagrangian? Is this kind of the same thing?
They're similar in the sense that the different pictures are equivalent. So in principle, we only need one picture. And that's why I don't feel bad about listing this postulate as in the Schrödinger picture. You can do it in the Schrödinger picture, you could do it in the Heisenberg picture, you could do it in the interaction picture, but the different pictures are useful for different things. And so they just make different things easier. But they are equivalent. So in that sense, yeah, it's similar to what you said.
All right, thank you very much.
Sure. Okay, good. Other questions on the postulates? Okay, now when people first learn quantum mechanics, they often don't learn it in terms of states. They learn it in terms of wave functions. Perhaps when you were first exposed to quantum mechanics, you were told that the wave function was what you should pay attention to. So the wave function has to do with the position representation. So you start, from our present point of view, you start with position eigenstates. Okay, which we label by a position. This is just a state where the particle is known to be at the position r. Okay, and then if you take the matrix element, R with the state you're in, that happens to equal psi of R, which you can write in lots of different ways depending on your mood. You might write it like that, or you might write it in spherical coordinates. I don't know that we're ever going to use cylindrical coordinates in this semester, but we could in principle. And so those are all different ways of conveying the information about what state we're in. And then in the position representation, the operator of position is just represented by the ordinary vector position, which is just a set of numbers. The operator for momentum is represented by minus I h bar times the gradient operator acting on functions. So conceptually, we should keep these straight. These are operators on this side. And even though we'll often pretend these are operators, these are really defined by their action on wave functions. So they're not operators on the Hilbert space, they're operators on a space of functions, which happens to be the representation of what's going on in the Hilbert space. Okay, and so then there are things like what happens if we integrate over the whole universe of the wave function complex squared? And to answer that, we can first put in the definition of a wave function to write it like this. Okay, so this was definition of wave function. And then a very common thing is whenever you're stuck or you don't know what to do, think about whether completeness will help you. And in this case, this is just begging us to use completeness because we've summed over a complete set of states here. And so this is nothing other than the norm of the state. So here we used completeness. Okay, and then if normalized, then that's just 1. All right, so of course there's much more to say about each one of these topics, but we're just doing a lightning review here. So I will not belabor that about wave functions and position representation anymore.
Sorry, Professor.
Yeah, go ahead.
I'm a little slow in writing. I fell behind again. You
Okay.
said that's that's the definition of wave function, right?
Yeah, definition.
Okay, I thought that was determinate. Okay, never mind. Thank you.
Good.
No, thank you. Yeah, thank you. That's much.
Yeah, and it's fair to slow me down by asking questions. All right. So let's list a couple of important theorems. Things that we'll sort of be using all the time, sometimes without even thinking about the fact that we're using them. So one is that all eigenvalues of a Hermitian operator or Hermitian matrix, which is a prerequisite for being an observable, are real. Now, if you have a Hermitian matrix, so if or a Hermitian observable, if A is Hermitian, okay, and you know a couple of its eigenpairs. So let's say you happen to know that A acting on some state gives you back alpha 1 times V1. And you happen to know that acting on a different state, you get V2. And you happen to know that they're different. So alpha 1 is not the same as alpha 2. Then those two states are orthonormal. Sorry, not orthonormal, they're orthogonal. They may or may not have norm 1, of course. Okay, so Hermitian, a Hermitian operator with two different eigenvalues, the corresponding states are orthogonal to each other. That's a useful thing to know. Okay, and another useful thing is, let's say you have a bunch of observables, A, B, and C, etc. Who knows however many there might be. But let's say they all commute. And because we need 2 words for every concept, this is also compatible. That's an exactly equivalent thing to saying they commute. Then you can make an orthobasis of common eigenstates. So common eigenstates just means it's simultaneously an eigenstate of each one of A, B, and C. And so we label them by their eigenvalues, however many there might be. And then there's the concept of a complete set of commuting observables. So this is not a theorem, this is a definition. A complete set of commuting observables is a very important concept in any problem that we do. If we can, we want to, as soon as possible, identify what the CSCO is. Okay, and that's just a list of such operators such that the states have no degeneracies. That means if I label the states by their eigenvalues, it's uniquely determined what the state is then. So this has no degeneracies. And is uniquely determined. If you think you have a complete set of commuting observables and you list at your state, look at your list of states and you realize there's still a degeneracy, it means that you didn't find all the complete set of commuting observables and you need to look for others. Sort of by definition, the physical meaning behind this is just that if you really have a complete description, then you should be able to tell any two states apart. And if you can't tell two states apart, then it means you haven't found all the observables. There must be something that allows you to distinguish them that you need to find. Okay, now when you do that, when we say that there's no I didn't spell degeneracies, right? When you say there's no degeneracies, it's still true that if I look at observable A by itself, it has degeneracies, and the degeneracy labels for A would be beta and gamma, etc. The degeneracy labels for B would be alpha and gamma, etc., and so on. But if I look at the whole list, then this uniquely determines the state. Okay, so for a free particle in 3 dimensions, there are different choices of the complete set of commuting observables. So one would be just the position coordinates, x, y, and z. Or we could choose the momenta. Or we could choose, and this is a very common choice, the Hamiltonian and the orbital angular momentum squared and the z component. Now, if you've chosen those, you can't add in L sub x because L sub x doesn't commute with L sub z. So you're done. So all of those things, but then if you have spin also, then you need 2 more, and those would be S squared and S sub z. Except that S squared is kind of trivial because the spin, total spin never changes. So this is trivial, never changes. But S sub z will change. Okay, and the fact that S squared doesn't change is just a statement that it's intrinsic angular momentum, that each particle has some amount of angular momentum that you can never get rid of or add to as a total. But you can change its direction. That's where the S sub z is coming. Okay,
I'm sorry.
so, yeah, go ahead.
Just a little slow. So that part where you wrote with spin, is that just for the momentum part?
No, that's for any one of these.
Okay.
Okay.
Thank you.
Sure. Okay, so now let's consider what are typical problems that one might encounter. Not just on homework, but in real life. Okay, and so one thing you might have to compute is what's called the expectation value of an operator. Okay, and this is really just a statistical measure of an experiment that you might do. So the expectation value of an operator in a state psi is you sum over all the probabilities for all the things you could have gotten in your measurement, weighted by the outcome of the measurement. And then that's equal to the expectation, it's equal to the matrix element of A within the state divided by the norm. And we often just write that as A within angle brackets, but then we can only do that if somehow we understand by context what the state is. By context means that we've all agreed previously what state we're talking about. So that's the expectation value. Another statistical thing is the uncertainty. So the uncertainty of an operator in the state psi, we write usually as a triangle or delta A, and it's just the square root of the expectation value of the operator squared minus the square of the expectation value. Those are not the same thing. And therefore, this is something that's typically positive, although it doesn't have to be, so it could be 0. Okay, and among the things we proved, there's this famous fact that the uncertainty in position times the uncertainty in momentum is always at least h bar over 2. And then for two operators A and B, okay, that's always equal to 1/2. It's greater than or equal to 1/2 times the magnitude of the commutator between A and B. Okay, and for position and momentum, we found several states that obey this with an equality. One is Gaussian wave functions, just a free particle that happens to be in a state where it's a Gaussian. Another was the coherent states of the harmonic oscillator, which are not energy eigenstates, but instead are eigenstates that minimize the uncertainties in position and momentum. Okay, so another question that one might ask, and this really comes about directly from the postulates, is what if you're in a state psi and you want to know the probability of being in a different state? That's a perfectly legitimate question. So if in state psi, probability of finding system in a different state, let's call it phi.
I'm sorry, Professor.
Yes.
I don't mean to interrupt you again. I apologize. That second statement right out under the delta X, delta P, where you wrote delta A, delta B is larger than or equal to alpha. I'm sorry, did you mention, or does that mean that H bar over 2 is equivalent to that AB, or no? Is that something independent of the above statement?
It's a generalization of the above statement. So, so if we go here, if A was X and B was P,
Okay.
then the commutator of A with B is I H bar.
Ah.
Okay.
Okay.
And so this is the first one is a special case of the second one.
Yes, that makes sense now. Thank you.
Okay, sure. Okay, so if we're going back to this, if we're in a state psi and we want the probability of finding the system in another state, so really we need an observable. If it's something we can answer physically, then there's an observable associated with it. And the observable in this case is the following operator. It's a projection operator. Okay, and it's Hermitian. It has eigenvalues 0 and 1. And you can show that it satisfies the orthonormality and completeness of its eigenvalues. And the probability associated with it is just the matrix element between the two states. Actually, I probably should write it the other way around, although it makes no difference. Okay, but it looks like that. Okay, and so that you've measured the system by asking whether or not it's in some other state. And after you do that, according to the fifth postulate, afterwards, the state has changed. It is now phi because you've measured it to be in that state. Okay, so it changed. Okay, and so this is an example of this deep fact that there are two different ways a state can change in quantum mechanics. There are, in fact, two kinds of ways a state can change.
Professor?
Yes.
Sorry again. Why were the E values 0 and 1 in the last case?
Oh, so it's just that you get an eigenvalue 0 if you look at a state that is orthogonal to phi, because then this thing acting on that state will give 0. Okay, and if it's not orthogonal to phi, then and it's an eigenstate, then you'll get 1. So this is something we proved back in Physics 660 somewhere in the notes, but it's actually sort of a 2-line proof, I think.
So were these sharing the same eigen, what do you call it? Were they in the same basis?
Which things are you talking about?
The psi and the phi, were they in the same basis?
Well, you can always write any state in terms of the basis. So
Okay.
phi is any state, phi is any other state. It doesn't matter whether they're basis states or not in this example. Yeah, so there's no requirement that phi is a basis state.
So you're saying if it's orthogonal, it's 0. If it's not orthogonal, it's 1?
The eigenvalues, if it's an eigenstate, yes.
Eigenvalues of that the observable?
That's correct.
How are you relating that to the probability of finding the system and state? So I think, okay, I have to review this. Never mind. Thank you. I think
so it's just that in order to answer a question like this question here, we have to know what an observable is that will relate to that question. And so this is just finding the observable or stating what is the observable whose measurement will answer the underlined question. Okay. And then here's the answer. Once we've identified that observable, then we measure this probability, which we know we're allowed to do. The postulates of quantum mechanics tell us that we're allowed to measure probabilities associated with observables, and so that's answering the question. Okay.
Thank you.
So what was I doing here? I was misquoting myself. So two kinds of ways a state can change. Okay, and one is, I want to emphasize that these are incontrovertibly different, and there's sort of no way that you can put them together into a single way. So one is measurement. By measuring the state, we changed it. And that's postulate 5. Okay, and how did we change it? We changed it by multiplying by a projection operator. Okay, and the projection operator is something that's Hermitian. Projection operators are Hermitian operators. The second way we can change a state is by time evolution. And that was postulate 6. Okay, but there we learned in physics 660 the way you do that is you multiply by a unitary operator. And so it's something like this. If we evolve from time t1 to t2, it's the same thing as multiplying by a certain unitary operator that we'll talk about more. Okay, but unitary operators are almost never Hermitian. In fact, when they are, they're usually very simple operators. An example of an operator that is both unitary and Hermitian is the parity operator, but that's not something that's complicated enough to give you any interesting dynamics, because it's basically just going to give you a +1 or a -1. And so in every interesting system, unitary operators are just different than Hermitian operators. And so time evolution, as given by postulate 6, is just not the same thing as measurement as given by postulate 5, even though both of them are ways that you can change what the state is. Okay, other interesting questions we can ask, or that you can be given. You can be asked, what are the allowed energy levels? Okay, and so there you're really just being asked to solve an eigenvalue equation, which will look something like this. Okay, and so there's no sort of shortcut to that. It's just something that you have to solve either as a matrix equation or a differential equation, one or the other, usually. But last semester, we pretty much have figured out all the cases that can be done exactly. And so a lot of what we're going to be doing this semester is approximation methods. So you often need approximations. There's just no way to do it exactly. And so we will be doing that, for example, in the helium atom, we're going to be doing it 2 completely different approximation methods for the helium atom, and we'll see which one works better. Okay, so that's, I think, it for today because we're out of time. We'll continue our review next time with a review of how do you solve for the time evolution of a state in practice if you know the energy levels. We'll discuss some classical problems that all of you should have memorized. Well, maybe not memorized, but you should be familiar with. And then maybe next time, maybe the time after that, we will start in on our first approximation method, which is stationary state perturbation theory. All right, so that's it for today. Are there any questions specifically about this lecture?
Professor, this last statement, matrix or differential equation need approximation?
Yeah, I should say often need approximation.
No, what does that mean?
It just means that you can't solve it exactly. So you have to, if you can't, if something's too hard to solve exactly, then you have to do some approximation method.
Oh, mathematical method to solve the what you wrote above, right?
Correct.
Okay, thank you.
Sure. All right, any other questions before I stop recording? All right, so